नमस्कार मित्रांनो, आजच्या या कोविड-19च्या परिस्थितीत आपण अशा रीतीने भेटतोय आणि अशा पद्धतीने आपण एक आर्टिकलचा अभ्यास करतोय. मागच्या वेळेला आपण इलॅस्टिसिटीचे संदर्भातले हुक्स लॉ वगैरे याचं इंट्रोडक्टरी डिस्कशन आपण केलेलं आहे आणि त्यानंतर आपण इलॅस्टिक कॉन्स्टंट्स विषयी सुद्धा बघितलं. नाउ we will see when we are applying a twisting couple on a cylinder, then what happens. Means that this is also one of the we can say, in other words, when we are applying a couple or a force on a cylinder, when that cylinder is clamped at one end and twisted at the other end. See, the twisting has been done to an angle of theta about its axis, and then the cylinder is said to be under tension. See what happens due to the elasticity of the material of the cylinder. There is a restoring couple set up in it, and this restoring couple is nothing but equal and opposite of the twisting couple. Friends, you can see here the diagram of this cylinder. See now, in this cylinder we having a length of cylinder is N, center is O, and see this AB is original position. Then after twisting it, then this cylinder takes the form AB dash, and here is the angle theta. Here it subtends the angle phi. The cylinder having a radius r. See now, here in this diagram we have discussed that the cylinder having a length L and having a radius r, and the material of that cylinder, it having a coefficient of rigidity, that is theta. See again, once again, the upper end of this cylinder is clamped one. Due to that clamping, here the twisting is possible, and due to which the couple be applied to the lower end in a plane perpendicular to its length. Then the twisting of this cylinder, just now we have been seen that it is twisted it through an angle of theta radius. Now in the position of equilibrium, the twisting couple is nothing but equal and opposite to the restoring couple, and therefore we have to calculate the value of this couple. For calculating the value of the couple, we have to see that the cylinder which we have been considered here, or which we have been discussed in the diagram, that cylinder consists of a large number of coaxial hollow cylinders. Here, see, the coaxial means the having a same center and different radius, and having a hollow cylinders. Here we will consider one such a type of hollow cylinder which having a radius x and the radial thickness dx, which is shown here. See now, we are here considering one cylinder, this having a center O and this radius x and this radial thickness dx. See now, OB, fixed one. And when we are going to give or we are giving a twist, then the formation of the cylinder, it becomes OB dash. Then each radius of the lower end, see, this is an important point. Each radius of the lower end is turned through the same angle theta. See here, each radius is turned through theta. Here the 3 is shown. Yes, this is theta. And now, but the displacement is greatest at a rim. Displacement is greatest at a rim and it decreases as the center is approached. At the center, it is reduced to 0. Means at its center, the displacement due to that twist is 0, but at the rim it is a larger one. And therefore, by this figure A, see now in this figure A, again we are able to see that here, if this is the initial position before twisting OB, it takes a position OB dash. And now in figure A again, AB is a line parallel to the axis before the cylinder is twisted. On twisting, the point B shifts to B dash and the line AB takes up the position AB dash. In this way, here this line takes the position AB dash. Now see, such that before twisting, if this hollow cylinder was cut along AB and flattened out, then it will form the rectangular plate ABC. See, if we have considered any such type of hollow cylinder, and if we are cutting it along the axis AB and we are flattening out, then it will form the rectangular plate ABC. But after twisting, it takes the shape of parallelogram A, B dash, C dash and D as shown in the figure. See here, here is the figure. In this way, see that cylinder, we have been cut it and flattened it, then it takes this original position A, B, C and D. And after twisting, what happens? A, B point shifts to B dash and here C shifts to C dash. And therefore now this is a line AB, that is L. Now here the angle through which hollow cylinder is sheared is therefore BAB dash. This is angle phi. Then BB dash is nothing but L into phi. And see, from figure A or B, you will get easily BB dash equals to X into theta. BB dash equal to X into theta, and X theta is nothing but L into phi, and therefore here we are easily calculate phi equal to X into theta by L. Obviously, phi will have the maximum value where X is the largest. That is, the maximum strain is on the outermost part of the cylinder. Just the statement we have been done here, you can see the statement. See now, each radius of the lower end is turned through the same angle theta, but the displacement is greatest at rim. decreasing at the center is approached. At the center it is reduced to 0. In that same fashion, here he says that the phi will have the maximum value where x is the largest, that is the maximum strain on the outermost part of the cylinder, and least on the innermost. In other words, we have to see the shearing stress. See, the shearing stress is not uniform all through, and therefore the angle of shear is greatest for the outermost and the least for the innermost. And by this, if we are calculating the coefficient of rigidity, that is eta, equals to, we know the formula, shearing stress upon shearing strain. Here eta equals to F upon phi. Here F is the force applied in the direction as shown in figure B. See once again what is figure B. This is the figure, and force is applied in this direction. Therefore, due to which this B point takes the position BB dash. In this way, here F equals to eta into phi, and therefore phi equals to x into theta upon L, because F having a value x into theta, and by putting it again here, F equals to theta into x into theta upon L. Here now the face area of hollow cylinder. The face area for the hollow cylinder having the formula 2 pi x into dx, and therefore total shearing force we have to calculate on this area. It is nothing but 2 pi x dx into eta x into theta by L. And by calculation, see, simple thing, 2 pi x square into dx into eta into theta by L. And therefore, we have to calculate moment of this force about the axis OO dash, which is shown earlier in the figure A of the cylinder, is equal to this much quantity, that is 2 pi eta of theta x square into dx into x by L. And see here, x and this x, we will get x cube, 2 pi eta theta as it is x cube, and dx by L. Now here for entire, we have to moment of this force. For calculating it, we will calculate total twisting couple on the cylinder. For getting an idea about a total twisting couple which is acting on the cylinder, we have to integrate the above expression between the limits x equals to 0 and x equals to r. See friends, here 2 pi eta theta by L x cube into dx between the limits 0 to r. Here this quantity 2 pi eta theta by L, we will take it outside the integration, and integration of x cube by into dx between the limit 0 to r, and by solving this 2 pi eta into theta by L, see here, by solving this x cube and dx, which is nothing but the x raised to power 4, and this integration of dx is nothing but the x, and therefore x raised to power 4 by 4, and between the limit 0 to r. Now 2 pi eta theta by L, See here, upper limit is r raised to power 4 divided by 4 minus this 0 is lower limit raised to 4 and upon 4 this quantity is 0 and therefore 2 pi theta r raised to power 4 upon 2l. And see if the theta we are having one radian, and then we have twisting couple per unit twist of the cylinder is C equal to pi theta r raised to power 4 upon 2L.